All right, it's about 9:30, so we'll get started. Today we've got a couple of, I don't know, 3 or 4 things we're going to do. One major thing and then a bunch of smaller things. So looking at our poll, well, there's only one vote in a poll, but the question was, have you made any modifications to your printer? The answer of one person was no. Maybe some other people chime in a minute. But that's what we're going to do today is we're going to make a couple of modifications that one that's super simple, like it's not even, I don't know, there's a little bit of work involved, but mainly you just have to buy the part. And then the other one that's a little more complicated. Both of these are things that you probably will want to do at some point, either because a part wore out or because you just want a different purpose for your printer. So the two things that fall into those categories are, one, we're going to do a bed swap. And if you'll remember, our printer has just the default texture, which is fine. This is the rigid one too, not the floppy bed surface. I don't really like the floppy one. I don't even know if they include it anymore, but this one's rigid, so it's a flexible plate, pretty good. The reason I don't like the floppy one, so there's one like this that's kind of a rubbery mat. If you have anything that sticks to it, or if your nozzle accidentally, sits on it too long and it's heated, or if it digs into it, it kind of ruins it. It'll deform it, and it just won't be flat anymore. So I don't really like the floppy mat if your printer came with that thing, just because I have to be super careful with it that I don't destroy it. The rigid one is fine, but we are going to make a change to our bed. But we're not going to really get rid of this one. The change that we're going to make is simple enough that we could still use this one if we want to. But what we're going to add is this one. So this is Idea Former. They're not the only brand. This is the one I found on Amazon. Let me open it and get it out of here. Oh, it's in another box inside this package. So here we have that. So let's open this and see what we have in here. This is a super easy mod if you're interested in this one. It's not, there is one little issue with it, and that is that if you don't have a bed sensor, which our printer does not have a bed sensor, there's no, usually the sensor's right up here to detect the surface of the bed. If you don't have that and you go switching out bed surfaces, they can all be different thicknesses, and you have to adjust your limit switch to account for different thicknesses of beds. So that could be one little issue that you have to deal with. So here's what's in the little package, and it's in a package. Let's open that up and see what's inside here and why I might want to change out the bed every now and then. Again, it does work a lot better if you have a sensor. It comes with a magnetic sheet that you can stick down that just fell on the floor. And this is what's inside the package. All right, let's get all this out of the way. Let's clean our magnetic sheet off, because this is sticky, so it's going to stick down on here, and if we want to, we can just, this is not magnetic, this is the original one, but it can just sit on it and we can clamp it back down with the little binder clamps that we had before. But this one is magnetic, and so it will sit there magnetically, and one side is a lightly textured PEI, so you can kind of see that it's got some kind of texture to it, but the other side is PEU. I don't remember what this surface is. This is a slightly different surface, but it's it has ridges like micro engraved in it. I'm not actually sure how they put them in there. It's probably stamped or something, I don't know, but it's a good surface. It doesn't stick quite as well as this surface. So this PEI material, this kind of gold material here, one, it's a little bit textured. This is one of the lighter textured ones. There's some that are way more rough. so that it embosses that texture on the bottom of your print, which is kind of neat. But for PEI, this material actually will, when you heat it up, it like bonds to your print to hold it down while it's printing, so you get really good layer adhesion for that first layer. And then when it cools down, it kind of lets go of it and your parts slide off of it. So not only does it impart kind of this texture on the bottom surface, which can be useful depending on what you put on the bottom of your print. Maybe that's actually the top of your print, you just printed it upside down. But it'll hold your prints down pretty well. This one, it does bond a little bit. I can't remember this material. I think it's PEU maybe, but I don't remember. Anyway, the purpose of it is that you print on this one and you get that pattern on the bottom of your print, which again could be the top or whatever. So it's the whole point is that you get this pattern, and there's a couple of these different patterns. This is kind of the random triangle one, but there's one that looks like carbon fiber. So if you printed with a dark, maybe a charcoal or a black filament onto one of the carbon fiber versions of these plates, it kind of looks like carbon fiber, at least on that surface. So it's a pretty neat one. You do have to be careful with this and the PEI, because your nozzle, if you don't get your nozzle height right, it can drag across here and actually scratch the surface. So we do have to be aware of that, particularly since it's likely that the combination of our magnetic sheet and the build plate might be a little bit different thickness from what we were at. They're close, but I think this combination is going to be thicker than this was. So what that'll mean is that we really do need to go and adjust our limit switch back here, because we don't have a bed sensor that's going to detect where the bed is at. In fact, maybe we will wait to install. Installing this is literally peeling the sticker, cleaning this surface. You can just do the same thing you've always done with your IPA, wipe it down, peel this off, and stick the magnet down. So that's the whole installation. I guess you want to get it straight or whatever, but there's nothing really tricky about installing this. But maybe we'll wait, because I don't want to tear up our nice PEI sheet. But all you would do is clean that, stick the magnet down, and you're good to go. You can still use this one, but it will be a different thickness, so you'd have to adjust your Z height if you don't have a bed sensor. We are going to add a bed sensor. In fact, maybe we'll do that next time, but so that we can easily take advantage of these changing bed heights. Because there is another thing you can do. You can add a glass bed, not magnetic, but you can clamp it down just like we've done here, but that's going to be even another thickness. So once we start wanting to print on different thicknesses of surfaces, then it's really pretty useful to have a bed sensor that will tell you where the bed is at, versus having to adjust this end stop every time you want to change the bed surface. So maybe we'll hold off on our bed swap for just a day, or 2 days I guess, but that's a really simple mod, and it adds functionality. If you don't already have a PEI sheet, or you don't have one of the textured, I can't remember, I'll have to look up the actual material, but if you don't have one of those, then it adds some functionality to your printer, and it's super easy to do, particularly if you have the bed sensor. All right, so we'll come back to that after we've put our bed sensor on. The actual installing the surface is super easy, so we don't even need to do that. Actually, you don't even need the magnet. You could just do what we've done already, and just use the binder clips like we've been doing, and just put this directly on the heat bed. Again, you run the risk of different thicknesses though, so you do have to be aware of that thickness issue. All right, so before we get to the other thing, we want to do a nozzle change. Let me show you a couple of filaments that I've got out here. Here's just one that's a cool color. So sometimes I get these samples. This is from Flash Forge. They also have, this is Nebula Purple. They also have one called burnt titanium, and they look really, really cool when they're printed. They're just PLA, but they have a, I don't know, it's a unique texture to them. I'm not sure what's in them. It does not say on here that you need a hardened nozzle to print them, but they do seem like they've got some kind of fibers in them. Maybe it's a ground additive that gives them a little bit of a rough texture that hides the layer lines, and they're a little bit shiny. So maybe it's some kind of, I don't know, mica or something that's in there. But Flash Forge, Nebula Purple, and Burnt Titanium are really cool colors if you just want some interesting colors to print. I will say that these the shinier filaments, usually the additive that they have added to the filament to make it shiny weakens it a little bit. So the layer adhesion is not as good. So if you're printing something that is meant to be structural, you may not want to use one of the shiny filaments, because I'm not sure what the additive is that makes them shiny, but it tends to make them weaker. So this one being a little bit shiny, it's not the shiniest of filaments I've seen. There are some that are shinier, but it's possible that this one would be weaker. That would be, if you're looking for one of the technical memos to do at the end of the class, that'd be interesting if you had access to a shiny filament and a regular filament, just a plain PLA, that you could test. Are they actually weaker or not? If you devise some way to test their mechanical strength. Or if you're at school, you can use one of the tensile test machines. So that would be interesting to see if it's true or not. It seems that way. Definitely seems that way, and I believe it's true, but I don't have any data that says that. So that's a cool filament. Let's see, and this one looks ordinary, and you probably can't read it, but this is a conductive PLA. So it has conductive material in the filament, but it's a PLA, so it prints like PLA. But I got my multimeter here. Hopefully you can see the screen on it, and if we measure the resistance, so that if it has a resistance, then it's some kind of conductive. Let's go maybe an inch or so, something like, I don't know, that's about an inch. We're not going to be super scientific here, but you can't see it. Let's get that. So 2.2-ish or 2K, 2000 ohms in about an inch or so of filament. So that's not too bad. That's pretty conductive. I mean, it's definitely more conductive than PLA by itself. This is a pretty interesting. It's more expensive because it's got a special property, so it's probably about twice as expensive as a normal roll of filament. This is only 500 grams, and I think it was in the $30 range, so it's probably more than twice a regular roll of filament. But it opens up some potential that you can do some interesting things. One of the things we're going to try, there's a student working this summer who is trying to print strain gauges onto other parts. So with some of the printers, you can do two different materials. You could do the process that we talked about last time. That's not exactly what he's trying to do, but some printers have multiple material capability. And so the idea is print a solid block of PLA or whatever, and then print a strain gauge out of this material onto the top of that, and see if you can measure strain with an embedded sensor. So if you can, then that's a pretty interesting thing. Now, this is not nearly as conductive as a piece of copper wire or anything like that. So it's not going to be ideal, but if it'll work, then that's pretty. That opens up some interesting possibilities. All right, so that's a pretty cool filament that you might be interested in at some point. And then one other filament and a topic about it before we do our main thing. Last time I mentioned lightweight PLA. I've used all of my lightweight PLA, so I don't have any more, but I do have this sample of lightweight ASA, and they look very similar. ASA just prints at a different range of temperatures than PLA, and remember I talked about ASA a little bit last time, but I said I hadn't printed any of it, and some of the cautions on it are that it's a little bit noxious. So we're going to need to do something with our printer setup before I want to print any ASA, but we have that sorted out. We just have to, have time to do it. But the idea with these, there's a lightweight PLA, and this one particular one is a lightweight ASA, is that as you print them, they actually foam up. So they expand depending on how hot you print them. So the hotter you print them, the more they expand. So they take up more volume with the same amount of printing being done. So the idea is, and some are pre-foamed, so they've already been expanded, and then you just print them. But the ones that I have used, the PLA ones, were not pre-foamed. So as you printed, they expanded. So you kind of adjusted your flow rate. So you would print at like maybe 40 or 50% flow rate, and then as you printed, the filament would expand and take up the rest of the space that you were expecting it to have, because you've reduced your flow rate to half of what you would normally think you would need, but then the filament expanded to twice its size. So I think they can expand up to 60%. So this lightweight ASA is capable of increasing its volume nearly 2.5 times. So you can, these density numbers probably don't really mean anything to you, but the part density close to 0.43 grams per cubic centimeter. But a regular PLA is about 1.1 grams per cubic centimeter. So somewhere in that range for density. So it can get much lighter parts. And so one of the things that you do with that, or you can do with that, and the thing I was doing with it is over here. Let's see. Oh, so in the YouTube description, I kind of ran out of space and to put some of these links, but they're in the Canvas description. So if you click on the lightweight PLA class 7 thing, then right here is the talking about the lightweight PLA and ASA. And then right here, there's a free, so you don't have to buy anything, at least to print it, other than the material, RC plane, and that takes you to here. And so this download a free model. This one is a free RC plane. So obviously RC planes need to be lightweight. So you can take advantage of this lightweight PLA or this lightweight ASA and print. I think it shows you, here's a exploded view of all the parts somewhere down here, I think. Maybe I didn't see that. Maybe it was just this. Kind of shows how all the different pieces are put together. You don't print it in one go. There are, what is this, 47 parts. Well, one of them's the pilot, but 47 parts to print in order to get this thing assembled. And if you have the electronics, battery and all that, controller, then you can actually fly the thing. So that's a pretty cool use for the lightweight PLA and the lightweight ASA. The ASA, again, it's going to be slightly stronger, a little bit more UV resistant, and heat resistant. So if you're in a situation where those matter, then it's going to have a little more of those resistances than the PLA. The downside is going to be that it you need some kind of enclosure and ventilation to print ASA. At least that's all the warnings say that. I haven't actually done ASA printing, but that's a pretty cool use case for some of these expanding foam type materials. I'm sure it's not the only use case, but that's all I've ever used it for. So if you want to try that out, or just print one piece of it, one section, then here is one that's free. I found another one. Plain Print has a free glider, so you don't even need any well, I guess you need the electronics to control the control surfaces, but you don't need a motor because it's a glider. Although maybe this one is not the glider. I'd found a glider somewhere. No, that's a glider. There it is. this might be the one that has the exploded view. There's an exploded view of the parts that you would need to print. Most of these are set up so that you can print on a printer the size of an Ender 3. You don't have to have an exceptionally large printer in order to print these. You can kind of see how, you know, they're broken into small enough parts that they would fit on a 200 by 200 or so millimeter bed size. This one uses some lightweight PLA, all the white parts. The blue are just regular PLA. They're you know, kind of a little bit structural, or they're smaller. It even uses some TPU, so some flexible material. We haven't done that yet. And then the carbon fiber rods to kind of make sure the wings have some stiffness to them. So those are some pretty interesting prints. They do take a while, a lot of parts to print, but that's a interesting use case for a particular filament. So I don't see anything in the chat. Still only one vote, but that's okay. Let us go to our main thing for today. So the main thing for today is a nozzle change. So I've got all the steps written out. These same steps are in the YouTube description, so you can look at them there. It's not complicated, but there's a little bit you have to deal with. Number one is you have to change these nozzles while they're hot, or at least you have to break them loose. If you don't heat up the nozzle and then try to unscrew it, then there's a decent chance that the nozzle is going to be seized in the heat block and the nozzle is going to shear, and then you've got a broken nozzle and half of it is stuck in the heat block. So it's a big issue to do that. So I have always recommended that you, number one, you know, preheat the nozzle. So we're going to go through this step by step, change our nozzle. You don't have to change your nozzle, but eventually, like even if you're using just plain PLA, eventually after some amount of printing, the nozzle is going to get worn. So I brought up the E3D nozzle. So E3D is a company that makes a variety of hot end parts among other stuff, and I brought up this. They actually have all of their design files for their nozzles in particular are online. So if you had the capability, you could just go make your own. But what will happen? Here's a cross section of the nozzle, and even with PLA, this will happen. But if you have a brass nozzle, which most of your printers start with a brass nozzle, is that over time, this bottom flat here will be worn because it rubs across the top of the surface as it's printing, and it will wear down this flat until you have a nozzle diameter that is no longer 0.4 millimeters. So it gets, it's a cone shape. So the more it wears, the wider that nozzle diameter gets. This will happen really fast if you print any of the materials that have particles in them. So potentially that that one I showed from Flash Forge, the shiny one, I'm not sure, but that one might be a little bit faster wearing. But certainly if you're doing any of the like glow in the dark filaments, or maybe some of the the carbon fiber filled filaments, those will eat up a brass nozzle really quickly. So it is a pretty high probability that at some point you're going to have to change a brass nozzle. Now if you've got a hardened steel nozzle or some other type of nozzle, you may not ever have to do this unless you just want to, but maybe you want to print with a different size nozzle. So your printer has 0.4 millimeters and you want to print really tiny stuff, and so you want to drop the nozzle size down to 0.2 or 0.3, so you want to change it for that reason. Or maybe you've got a giant printer and you want the largest nozzle possible so that you can print giant parts faster. At work or at school, we have a printer that has a 6-foot by 4-foot bed on it. So you probably want a larger nozzle on that printer so that you're not printing for months at a time for one part. So there might be other reasons why you want to change this nozzle. Maybe you just want to print more abrasive materials and you need a different material nozzle. So the brass, so I put further down here, I put a list of You know, brass nozzles, that's kind of your default, but they make stainless steel, they make hardened steel, they make ruby tip nozzles, diamond tip nozzles, tungsten carbide, silicon carbide, probably other kinds too. There are some that are brass that are coated with nickel. So there's all kinds of different materials you can use for the nozzles, and they continue to evolve with even more types of nozzles. So we're going to put just what I have. So I don't currently here have a large selection of nozzles, but I do have this selection. So where's it at? Have this selection. So this is actually a Creality set of nozzles that I've mixed some others in. So normally what I would do, these black ones here are hardened steel. Those shiny ones, you might think they're stainless steel, but these are not. These are actually brass with a nickel coating on them. And then there's a brass nozzle in there. So most of these are 0.4 millimeters. This one in this corner, or well, I guess not a corner, but this one over here is a 0.8 millimeter nozzle. So it's twice the diameter of the 0.4. Everything else, I think this one in the hardened steel, the tiny one up here, I think that's a 0.3 or a 0.2, I can't tell. Normally these nozzles have writing on the side of them. Well, I don't see any writing on that one. Maybe I'm just not seeing it. So we would need a pin gauge to figure out how small that one is, which I don't have here at home. I'd have to go to work to find that. But it definitely looks smaller. So I'm going to say it's a 0.2 millimeter nozzle. I could probably look up this set and see what comes in this set. It's a smaller one. Normally what I would do is I'd put a 0.6 millimeter nozzle, because I'm not normally, with these kind of FDM printers, I'm not normally trying to print super high detail parts, and I am usually trying to print larger parts. So remember last time or earlier I said that in general a good range of layer heights for your prints is 25% to 75% of your nozzle diameter. So if I go to a 0.6 millimeter nozzle, I can still print 0.2 millimeter layers pretty easily. If I want that, I can't really go much below that and have a lot of accuracy, but I don't have a 0.6 millimeter nozzle, so I'm going to put this 0.8 in there. Those are harder to deal with because they just have such larger volumes of material that have to flow through them. In fact, if I go back to that E3D site, it shows some of the, let's see, where does it show? Oh, flow rate. So here's a document. Oh, hold up. Here's a document on flow rate. And we can see for a point, well, this is a 0.8. We'll say brass, although it's not brass. Volumetric flow rate is 15 cubic millimeters per second. That's not significantly different because the limiting factor is not just the size of the hole in the thing, but how fast can I melt the filament. So right here they're showing that they're melting PLA at 220. That's really hot for PLA, and they're getting 15 cubic millimeters per second. There are other, at least E3D has what they call the volcano and the super volcano, which, you know, this super volcano is here's a 1.4 millimeter. That's nearly the size of your filament, you know, and it's got a 92 cubic millimeter per second flow rate. So you can pump out a lot of filament. Can you get it put in the right spot in time? I don't know, but that's a lot of filament. All right, so just for the purposes of our demonstration, I am going to change this nozzle with a 0.8 millimeter because I don't have a 0.6 millimeter nozzle currently. So let's follow our instructions here. So number one, oh wait, that's not number one. Number one, preheat the nozzle. All right, so we got to turn our printer on, and I'm going to just do PLA temperatures that's fine. So temperature, preheat, PLA, and just the nozzle. We don't need the bed preheated up, so we'll just do the nozzle. So number 2 is actually remove the filament. So if you have filament loaded in your printer, go ahead and take that out once it gets heated up, because it will be a big gummy mess if you take the nozzle out and there's filament in it. So that's going to be a pain. So I'm waiting for it to heat up right now, and then we'll take the filament out and carry on. Let's see, let's go to our overhead view. So I just went over here and did the preheat PLA nozzle, and it's at 140 or so right now. That's a little too low for preheating, or for removing the filament. I need to get it up around at least 180 before I can take the filament out. $170. All right, so remember, I'm going to operate the feeder mechanism back here. Well, kind of off the screen of what we're looking at right now. I'm going to push the filament in a little bit and then pull it out. Okay. And then got a little ooze out of there. That's what I wanted, though. I wanted that to come out. My filament, this was that red. You know, remember it was brittle. It's still brittle. So we actually have a way that we can deal with that brittle filament if you do have a whole roll. Now this is just this little partial roll, so it doesn't matter, or it doesn't bother me that much. We'll get to that some other day. But we've got our nozzle heated and we've got the filament out. Let's look up here. So now everything down here is 200 degrees, but we need it that way at least while we're breaking the nozzle loose. So I'm gonna try and not, you know, touch any of this with my hands. So I've got to get that rubber silicone sock off of there. Okay. Now it's probably going to be easier if I take this cover off. Just for one, I can see better. I'm having to look underneath everything right now. So I'm going to take these 2 screws out. There's one. The other one's right above there. It's just off the screen. I'm going to take that off just to have better access. I'm going to try to not lose the screws. Now this fan is running continuously, so you have to be careful not to accidentally get your Allen wrench in there or something like that. You'll break those fan blades really easily. So we can just set this kind of off to the side. Something like that will work. All right. So there's our heater block. Those big red wires in the background are going to the heater. That's the end of the heater right there. The thermistor is on the other side. It has really fragile, tiny wires, so we want to be careful of this side over here, because those wires, we don't want to damage them at all, and that can be an issue. So let's go back to our steps here. So we remove the filament. So secure the heater block. So again, the heater block is our silver, so it's aluminum block right here, 200 degrees currently. So we can't just hold it with our hands. I've got a giant crescent wrench, or a 10-inch crescent wrench here, and I'm going to just use it to, hopefully I can use it to kind of hold the heater block in place, something like that. Now this one does have a screw here and a screw here that sort of hold it in place, but if I don't hold the heater block in place, then what's going to happen when I go to unscrew the nozzle here is that there's a chance I will twist the heater block. You can kind of see, maybe, it is connected to the heat break in there. The heat break is a really thin piece of, in this case, it's steel. And it's pretty thin walled, and you can twist it and kind of crumple it if you're not careful. So that's what I'm using the crescent wrench for, is to hold the heater block while I'm undoing the nozzle. Now, your kit came with these little guys. You know, I don't know which one, but something like this that will fit the nozzle. None of these do, so it must be the other one. Must be this one. And technically, that will work. But I do have, since I have it, I have this tool. That fits on the nozzle. And so I'm going to use this one just because it gets my hands a little bit further away. This little guy gets hot really fast. So that nozzle is 200 degrees, and it does not take that long for the heat of the nozzle, to get all the way through this thing, and this heats up pretty fast. So this one takes a little longer to heat up, and I'm a little further away. So I'm going to use it. So you'll probably not be able to see a whole lot while I do this because I've got to have my hands all in the way, but let's just do this. Have to find the right position. All right, so that was super easy, and the heat block did move a little bit, but it wasn't too bad. Now you can go ahead and start cooling things down. So temperature, nozzle, we can drop it back down to room temperature or 0. That little guy can kind of cool things off, because we've got to take this nozzle out, and then we've got to get our new nozzle. So I'm going with the 0.8. Did I lose? Oh, it's down here. Now this is a well, we're on this camera. This is a brand new nozzle, so I don't have to really worry if there's anything wrong with it. But if you're replacing with an old nozzle, sometimes there'll be, filament kind of on this surface. You'll want to clean that off. Hardened filament is, you kind of have to sand it off of there or something to actually get it removed. But this is a brand new nozzle, so I am going to make sure that there's nothing obviously wrong with it. I've had one nozzle in the past where the hole wasn't drilled all the way through, so it was, I don't know, it was just a manufacturing defect. Sometimes there can be a little burr inside that hole, which is a problem. So this one looks fine, and it's been a long time since I've seen anything wrong with a nozzle. Oh, by the way, replacement nozzles, other than the diamond and ruby kind, are pretty affordable. We'll look at them on Amazon so we can see what the prices are. So we're still hot over here, but we're not crazy hot like we were. All right, so looks like there was still a tiny bit of filament stuck in there. You can kind of see that's the kind of stuff we have to clean out before we use this nozzle again. And all right, it's touchable now. So, but if I wanted to use this nozzle again, it'd be better if I got rid of that filament that's in there. I could get it out with a lighter, heat it up and let it ooze out. Some filaments can melt in different chemicals. PLA does melt in a chemical, but it's a really bad, nasty chemical, so I don't want to use that. I probably just won't ever use that nozzle again because I have lots of brass nozzles, just not here. So here's our new one. Now it says we're at 61. All right, so it's still warm, but it's not bad, because now I need to thread this guy in the hole, and there we go. I'm going to get it just finger tight. So that's not enough yet, but now I need to heat it back up. Oh, well, let's go through our steps and make sure I'm not forgetting anything. So let's see. Unscrew, we did that. We checked the nozzle was clean. We cooled it down. All right, so it's cool, you know, warmish right now, but it's not 200 degrees. So we screwed the new nozzle in by hand. Now we've got to do the hot tighten. So, or hot seating, or whatever you want to call it. I've got the nozzle like pretty tight, hand tight. So it's butted up against, hopefully, the heat break threads inside there. But it needs to be a little bit tighter. And what I need, you know what I should check? I should check that this nozzle is the same length as the one I just took out. Let's do that real quick. So let's go to the overhead for that. It's a better camera. All right, so the threaded part of our new nozzle actually looks shorter. Yeah, it looks, all right, so that could be a problem. I really, let me look at it closely. It's hard for me to see it on the camera. No, I think they are. I think it's just a optical illusion. So I think they are the same length. If they weren't, if these threaded regions weren't the same length, we might have to go to, let me get some software here to show you what I'm talking about. Let's see, we're over here. Let's go to this. All right, so we were over here last time. We talked about that a little bit, and glass transition temperature and all of that. Inside, let's look at what's inside this heat break, or heat block actually. So, crawl. So here's our heat block. That's the thing that has the heater in it. So that's the block of aluminum. And then our heat break comes down inside here. And it's a hollow, it's a hollow tube. Really thin walls. That's where the filament comes down inside there. So heat block is that guy. Heat break is that guy. So heat blocks usually aluminum, heat breaks usually stainless steel, although you can get like fancy titanium ones and tungsten ones and all this other material. This is threaded into the heat block. This heat break is the part that if you don't hold the heat block while you're unscrewing or tightening, then it's possible that you can mess up your heat break. So if my nozzle doesn't come up and make contact right here, then there's a good chance that I will have leaks out between that gap and out. I'll get filament coming out, it'll go down the screw threads and it'll come out over here and over here. So if you see filament coming out the edges, like not like out of the nozzle, but between the nozzle and the heat block around the edges of it, then probably what happened is the nozzle threads, or well, not the threads, but the back side of the nozzle, this little surface right here, did not make good contact with the heat break, the bottom of the heat break. So I do think that this nozzle is the same size. It didn't look like it at first, but Now that I looked at it closer, I think it is. So we should be okay. So I'm going to try and find where it goes. It's hard to do without seeing anything. There we go. All right, so we're back to hand tight. All right, now it's all cooled down. We need to heat this guy back up. Okay, because I need to make one last little turn, not a whole turn, make a half of a turn, quarter to half turn on the nozzle while it is heated up to seat it against the heat break. If I don't do that, I probably will get leaks coming out all around the nozzle, and that's going to clog up stuff. It's going to be a big problem. So this little hot tightening or heat seating or whatever you want to call it is kind of the last steps. And then while we're waiting for it to heat up, just know that there are a couple of other things. It's possible that you might have to go re-level your bed, not necessarily level the bed exactly, but adjust the Z height, because different nozzles can be different lengths. I am replacing a Creality nozzle with another Creality nozzle, so they're kind of all the same. But if I changed out to some other kind of nozzle, they make like little pinpoint nozzles with really needle type ends on them, and they make these shorter ones. So if I've changed that, then I might need to readjust my Z height. Let's see, clean it off. If there might be some particular specific instructions, I can't think of any right now, but it's possible that yours come with any special things. But the biggest thing is that the height of the nozzle might have changed. Ours shouldn't have, because we're just replacing with a Creality nozzle with a Creality nozzle, so it should be okay. All right, let's go back and finish up our change. So we're all heated up. I'm going to hold this back up again. I've got it hand tight, and I want to do another half-ish. Well, no, yeah. Based on that, how that feels, I did about a quarter turn. No, like an eighth of a turn, maybe a quarter of a turn. Not a lot. You can kind of feel when it just won't turn anymore. You saw I went from there to there. That's about what I did. So that's an eighth of a turn is what I did. Somewhere in that range. We do need to put our cover back on there. We can let it cool down if we want to. Maybe we'll leave it hot just to maybe want to print something. We've got some time to do some other things. Later on, we're going to change this whole hot end, so we'll come back to it. Oh, you know what we can do? I just put a 0.8 millimeter nozzle in there, so I can't just go normally print with a 0.8 millimeter nozzle. And I changed the material of the nozzle. So it was brass. This one is hardened steel. So when I change the material, don't forget this little guy. This is the harder part. Let me put this on and I'll tell you about the materials. Okay. We can come back over there, I guess. So the brass to hardened steel have very different thermal conductivities. So the PID tune is definitely not going to be the same as it was before. So let's see if our printer has PID tuning built into it. So configuration. Advanced settings, maybe. Temperature. There we go. Auto PID E1. So E1 is going to be in this printer the extruder 1. A lot of times it's actually E0, but they're calling it E1. So I am going to click that. I'm going to tune to 205. So that's my normal PLA printing temperature. So I want to tune the PID to a temperature I normally print at. So I normally print at 205. So that light's blinding me. It is doing the auto tune now. So it's heating up and it's going to cool down. I'm not sure how many cycles it's going to do, but normally there's at least 3 cycles, but maybe it does 5 cycles of heating up to 205 and then down. And I want to do this because I know for sure that I have different characteristics of my nozzle. Now, if I went from a brass nozzle to a different size brass nozzle, that's probably not worth doing a PID tuning, but I went to different materials. So I'm going to do the PID tune. It doesn't take long. When I was talking about it earlier, I was using Printerface to do the PID tune. So we actually connected to the printer through a USB cable and used our PC to do this same thing. But most printers these days, you can go directly through the menu here and do the PID tune. The only thing I don't get is I don't get a readout of like anything other than auto PID. So I can tell that it's heating up and cooling down, and that's it. So we'll let it do its thing, and it should give us some new values for, I should have actually written down the old values for P, I, and D. They were in the screen here, but I didn't do that. Oh, all right, so Ender 3 ready. So just to be sure, I'm going to go to Configuration, and I'm going to go to Save Settings. Sometimes settings that you do on the control panel here are automatically saved, and sometimes they're not. But you can always go to the control panel, usually in the configuration menu, and just save the settings. That way the new P, I, and D values should be saved. Let's try and print something. So I don't really have a particular thing in mind to print. I don't even have Cura open, so let's open Cura. And maybe we'll just print a calibration cube. Just see where we're at. Oh, we need some filament in there. Let's print that shiny filament. Where'd it go? Here it is. So the chameleon. It's another one of those that is not on a spool. I only have a little bit of it, but since we're just printing for a second, I don't think we have to worry about the tangling issue. All right, it's gotta, I gotta untangle or untie it. All right, so let's find the end of it. I think this is probably the end. It is. Are we heated up? I think we are heated up. No, we're not. We got to preheat again before we can load our filament. So the end is cut off square. I'm going to cut it at an angle. It's really pretty crooked too. So when they're curved like that, it's usually best to try and straighten them out to get them to load a little better. Oh, lost it. Okay. I'm going to cut it off at an angle, and let's see if we can load it. Have to do a little twisting to get it to go in there. So, all right, so see, without a spool, we're already like all tangled up here. Since I have this one sitting right here, I am going to put it on a spool just to try and prevent some of the tangling from happening. because it looks like it really wants to tangle up pretty badly. So I'm just doing that. Okay, all right, so let's put a little bit of filament through our nozzle. And let's motion, move axis, extruder, and let's do, I don't know, 30 millimeters through the new nozzle. I can already tell, you know, look how much thicker this thing is compared to previous. I don't think I have a previous. Here's a little piece. So look at the difference in, I don't know if you can tell, but you can't even see the red one there. So it's definitely going to be bigger. All right, Cura. Let's go to Cura. Oh wait, no, we need this one. And first of all, we need a 0.8 millimeter nozzle. We will discard the changes. Let's do a cube. So we just have a 20 millimeter cube down here. We have a 0.8 millimeter nozzle, so what layer height do we want to try here? 0. Do we want to do 6? Let's do 4. Let's do 0.4. So that's kind of right in the middle of the 0.8. Now, one thing is when you have these bigger diameter nozzles, you really don't need many walls to make the part strong because your walls are so much thicker now. Like 2 walls are over a millimeter thick. So we'll go with 2 walls. We definitely don't. Let's do 3 top layers. If I do too few top layers, then they'll sag and they won't look very good. So let's do 3. Let's do only 2 bottom layers. We could probably get away with 1 bottom layer. It's 0.4 millimeters thick, so we could probably get rid with just 1. But we'll do 2. Infill at 20. Printing temperature. So we are having to melt filament faster. So let's at least go to 205. Well, not 2050. That would not be good. It actually wouldn't let me do that. There are firmware limits on how hot you can make your printer, so that's a good thing. We need cooling. We'll have that skirt out there. Hopefully nothing's changed with that. So let's slice this guy. 11 minutes. So let's preview just to see what we're dealing with here. Look at this thing. I mean, that looks pretty solid. Now let's see if I can remember in Cura how to do this. Maybe Cura. Oh, all right. So here's the flow. So I'm in the preview, and here is a flow under color scheme. So I'm in color scheme. Change it to flow, and so it looks like everything's kind of green and cyan color. So 8 millimeters cubed per second. If you remember from the E3D website, the 0.8 millimeter style nozzle can flow around 15, so we should be okay. We're not trying to ask it to flow so much that it can't actually do it. Now they were testing at 220, so we were only running at 205, so I don't know. But let's save this and see what happens. Where's my little, here we go. Okay, save to, I'm still using that SD card that I told you not to use. I'm just going to keep using it until something goes wrong. Because none of the prints on this printer actually, you know, matter. So they're not for any particular purpose other than a class. So if something goes wrong, it's not that bad. Alright, print from TF card. Oh, what did I call this? It says it's untitled. I guess, oh, there was already, all right, so I think this is the right one. Although, let me check because it's showing, yeah, 205. All right, so I think this might be the right one. It's got the bed at 50, which I had. We'll know pretty soon enough if this is the right file or not. I think there was already one on there called Untitled, and that's why it was looking different than I expected. It's actually cooling the bed down right now. I had the gantry really high up to do the nozzle change, so it's taking a while to get back down to a normal height. So remember, I did do a nozzle change, so it is possible that this nozzle is a different height than the old one. I don't think it is, but I do need to be careful of this first little bit here to make sure that things are coming out clear. There's our first bit of filament. It looks good. It's really thick, but it looks good. Okay, it is the skirt for a cube, so I think we got the right file. So let's see if the nozzle camera is. Let me show you anything. I don't know if I can get it the right height for looking at it or not. Let's see. Maybe if it used to be a little bit higher. There you can kind of see what's going on. A little bit dark in there though. See if we can get some more light. Yeah, you can't really see much of what's going on. I can't see much of what's going on either. But it does look like it's printing okay. You may find that you have to print a little bit slower just to be able to melt the filament fast enough. You could check this flow rate thing. Like if we're currently at 50 millimeters per second, if I try to print at 75 and slice it, now they changed my scale over here, so now this is in the 12. I'm getting close to the maximum flow rate, so I'd probably have to bump up the temperature. So you do have to be careful. Flow rate is a function of the nozzle diameter, the layer height, and the print speed. So it's a volume, basically how much volume of material needs to come out of that nozzle per second. And so if I print faster or print thicker layers or thicker walls, then I need more and more filament to come out of the nozzle, and that might mean that my nozzle just can't deliver that much filament. It can't melt it fast enough. So you do have to be aware of that. In Prusa Slicer, which we haven't used, Prusa Slicer actually lets you limit the flow rate. So instead of just viewing it like in Cura, you can actually say, I don't want to print with anything more than 10 millimeters cubed per second. And so it'll slow down anytime it needs to, if the required amount of filament would be more than whatever you set as your limit. Cura just lets you view the flow rate. It doesn't let you have it as a threshold. Let's go back to nozzle cam. You can start to see, it's already built up its own layer. It doesn't tell me a layer number. It's already 3 millimeters tall though, so it's going pretty fast. It's about a quarter of the way done, a little over a quarter of the way done with the print. So you can start to see that you can get faster prints now that you're not going to get the resolution, because the layers, I put this at 0.4 millimeter layers. I could have gone up to, this is a 0.8 millimeter nozzle, so I could have gone up to a 0.6 layer height if I really wanted to push the limits of what I thought it could do. I'm not sure. Let's see what our flow rate would need to be. So 50 millimeters per second and 0.6 layer height. Let's see. Yeah, that would be close. That would be close. It'd only take 8 minutes to print, but it'd be close on being able to provide enough flow rate. Hold on. Let's I gotta put my light somewhere so I can let go of it. There we go. If we go back over here, did I put it in? Oh, I think I put it over here. Let's see. Yeah. Here. So back in here, there is a flow rate test, and there's and even on that E3D site, they show you how they calculated flow rate. They did a certain type of print, and it gradually increases the flow rate. It basically increases the speed until it fails, and that tells you where your maximum is. But there is this. Let's see, where's the link to? I want to open this in a new window so you can actually see the link to it. Oh, well, it just keeps opening it in. Oh, here we go. So here, this link, can you see? You can't see that. I'll put it in the chat so that it shows up there if anybody wants to see it. So this is a link to, basically, it prints a pattern of little blobs, and you can go and, if you have a sensitive enough scale, so you do need a little a scale that can measure, you know, tenths of grams or hundredths of grams, then you can weigh these little blobs, and it will, the pattern is, all right, this amount of material at a certain speed, and you'll see the if you plot the weights of those blobs, you'll see it taper off, or it won't be able to deliver the amount of material that you're asking it to deliver, and you can figure out your maximum flow rate at different temperatures with a given nozzle, so that you're not ever stuck in one of those situations where you're asking it to do too much. So that's a different way than what the if we go back to the E3D site. Let's see. So where's E3D site? It's down here with the nozzle data sheet. Oh, it's in, please see this document. And then down here they show their testing procedure, and they print this pattern basically, which is a little bit easier to do. You just have one print, and it's a single wall, and you basically print it until it can't keep up anymore, and that will tell you where the maximum flow rate is. So that may be a little bit simpler way. I probably need to do that with this nozzle because I don't know. I'm assuming it's around 15 based on this data. It's not brass, but I'm not printing that hot, so it's probably less than 15 cubic millimeters per second. So maybe it's 12. I don't know. I need to find out. Let's check our print, see how we're doing. Yeah, look, it's been, I don't know, a few minutes. Does it tell me? It doesn't tell me how long it's been. 6 minutes? No, it's been 8 minutes. And we've got over half of our cube built. It's a little bit blurry, but you can kind of get the idea of what's going to happen there. It looks like, looking down at it, it actually looks really pretty good for a print. I'd like to finish it so you can see it up close, because I think it's actually going to be pretty nice. And you do have to be okay with the visible layer lines for sure, because the thickness of these, I did what, 0.4, and you're definitely going to be able to see the layer lines. So some people take these larger nozzles and print really thick layers like 0.6 or whatever, and the whole point is that you can see the layer lines stacked one on top of one another, and you can get some pretty nice looking prints, but it's not going to be what you normally are thinking of with your 3D printer. Says it has 5 minutes left. Let's see. Oh, we were going to look at nozzle prices. Let's look at nozzle prices. So I'm just gonna look. I usually get Amazon prices. So FDM nozzle. So this one, wow. All right, so this is a particularly good one. $30 for a single 0.4 nozzle. This is Slice Engineering does make good stuff. They are usually more expensive because they've done some particular fancy things. So in this one, they're saying great thermal performance. So the nozzle I'm using, the hardened steel one, it's not really great thermal performance, at least not compared to brass. So I'm not sure what they've got going on here. Maybe it does have some kind of coating on it that's anti-adhesive, so basically it flows cleaner. So $30, but here's kind of your set of brass nozzles, 7 of them for $10. Here's a whole bunch of 0.4s for $11. Let's find a hardened steel. Here's a set of hardened steel for $12.99. If you are looking for a nozzle, make sure that it has the right thread pattern for your particular printer. Or usually what they do now is they just show it's compatible with, and it will fit your printer. But some of them just tell you what thread pattern. Like this one, at least the picture, definitely looks like this is a much longer set of threads. So if you went and screwed this nozzle into a Ender 3, regular Ender 3, it looks like it's going to stick out much further than the previous nozzle you had in there, because the previous one kind of looked like this pattern. So you do have to be a little bit aware of those kind of things. Here's that diamond tip nozzle. So this one, the little black tip here is synthetic diamond, and this thing basically never runs out. And pure crystalline, or this crystalline diamond actually is very heat conductive. So these things are actually really good, but it's $100. So I have not bought one of those. The ruby, this is actually a good price for a ruby tip nozzle. So the same idea, except you can kind of see the tip of it is a ruby. So those are anti-wear and still have good thermal properties. So here's the kit that I have. Here's the set that I have that I just got the 0.8 from. So from here, I will probably try and find some 0.6 nozzles, just because that's what this is what I normally use, is something like this, a 0.6 millimeter nozzle. But the 0.8's working fine right now. We'll print some stuff off with it just to see how it works. But it looks like that tiny nozzle that's in this kit is a 0.25. So maybe we'll put that in someday and try to print really thin layers. We're done over here. So there's our cube. Oh, it's still doing its thing. I'm not sure why it needs to do all that, but it is. So the bottom layer, I could use a little more squish. It's a little bit far from the bed, but in general, it's pretty good. You can kind of see some bulge. I can see, I don't know how well it shows up, but there's some bulging around the first layer. So the first layer is not going down quite right, and the top layer. So anytime I'm doing solid layers, it seems like it bulges out a little bit. So that's something that a flow rate type of issue I need to adjust. But overall, it looks pretty good. And I don't know if you can see how well you can see the layers. I don't know if I can get it to focus on that. It's getting some weird line artifacts, particularly with the shininess of the filament there. So that's kind of what you get with the 0.4 layer height from a 0.8 nozzle. There you see that X, the shadow of that X. That's the infill showing through in there. So sometimes if you see those patterns like that, that might be your infill showing through. That's what it is on this one. So I actually don't like, I don't mind that at all. I actually kind of do like it, other than the top layers and the corners kind of bulging out. So it needs some tuning, which I have not done any of. That PID tune we did was the first tuning this printer's had at all. So I haven't done any tuning. Maybe we can work on that a little bit next time. All right, I think we're out of time for today. We'll be back Friday, I believe. So 9:30.